Welcome to an application with variation involved. The braking distance d in feet varies directly as the square of the speed for a car traveling at s miles per hour. A car traveling at 60 miles per hour requires 226.8 feet of braking distance. Find a complete equation of variation to model the situation. I encourage you, please pause the video, give it a try on your own, and then restart the video to see if you get the same thing that I do. When I read the first sentence, I come across the braking distance d varying directly. I need the type of variation. I need the first variable, the type of variation, and then I need to know the second variable that we're working with. And the second variable is s, but it's the square of s, so s to the second power. When we have direct variation, it means that our model is going to involve multiplication of the constant of variation and the square of the speed in this case. When I go to write the generic equation, it should read d equals ks squared, or k times s squared. That takes care of the first sentence. Then I have a car that travels at 60 miles per hour and has a certain braking distance. 60 is the value for s, and 226.8 is the value for d. Those get substituted in. 226.8 equals k times 60 squared. 226.8 equals k times 3600. To solve for k, divide both sides of the equation by 3600. And when I do that division, I get 0.063 for a k value. For the complete equation of variation, I need to put this k value back into the generic equation. Our specific equation should read d equals 0.063 times s squared. This is our complete equation of variation. Second part of this problem, use that model to find the braking distance for a car traveling 70 miles per hour. 70 is a speed. In our equation that we just worked so hard to find, d equals 0.063 times s squared, we will make the substitution. d equals 0.063 times 70 squared. When you finish that calculation, you will get 308.7. This is supposed to be a braking distance, and if you look back in the beginning of the problem, braking distances were measured in feet. 308.7 feet for this car to stop. Let's check for reasonableness. This is supposed to be a direct variation problem, so that when your speed increases, your braking distance should increase. We had a car in the beginning that was traveling at 60 miles an hour, and its speed increased to 70 miles per hour. The original braking distance was 226.8 feet. That should increase when the speed increases. And I think that that's what happened. When we come back down here and check our answer out, 308.7 feet is greater than the 226.8 feet that we started with in the initial scenario. So this one is done.